Anubhav, are you good? Are you ready?
Yes. Thank you.
No, I'll introduce you. I just wanted to make sure you're ready.
Yeah.
We are recording, by the way.
Great. Awesome. Well, it's a great pleasure to have Anubhav Mukherjee that's going to tell us about exotic surfaces in the family Bauer-Furuta invariant.
All right. Yeah. Thank you very much. It's a great pleasure to visit virtually again. The great thing is that I gave my first talk at UGA. So that was maybe over a year or so back. And now, yeah, this is not technically my last talk as a grad student, but almost my last talk as a grad student. So yeah. So yeah, it's very exciting. And thank you for inviting me. And today I'll be talking about my joint work with Jianfeng Lin. I'll try not to talk too many technical things and try to give an overview on this problem and try to motivate people for some of the things I worked on. So let's start. So also I'll be writing the whole time, so maybe I will not check the screen. So if you have any question, you can feel free to unpause and ask directly, and I'll be happy to answer or try to answer. I'm not sure if I can answer or not. All right. So the main topic is that you want to understand some kind of thing in four-manifold theory. So in four-manifold topology, understanding of exotic phenomena and I'll define shortly what is the meaning of exotic here. So understanding of exotic phenomena is one of the main interest of study. So by exotic here, I mean that those phenomena that are true in topological category, but not true in smooth category. So this topological category versus smooth category dichotomy doesn't appear in dimension 2 and dimension 3. There are some great work that says that in dimension 2 and dimension 3, and definitely in one dimension, that whatever topologically true, most certainly true smoothly. So this is the lowest dimension where this kind of mysterious phenomena occur, and so that's the reason for manifold is such interesting. Okay, so now what are these kind of phenomena? So there are three main phenomena that we are actually very interested. One is called exotic smooth structure. So by exotic smooth structure, I mean that the two four manifold X. Oh, and in this talk, everything I'll be talking about four manifold. So X and X prime are homeomorphic, but not diffeomorphic. So this is one thing. The second thing is that exotic surfaces. So we call a pair of surfaces sigma and sigma prime inside X are exotic if there exists a topological isotopy in X that carries sigma to sigma prime, but no such in smooth way. Okay, So the reason surfaces in four manifolds are interesting because it's kind of the codimension, it's kind of the middle dimension object in four manifolds. So there are some deep results which was known before, in a sense that for simply connected manifold, that the topology is somehow determined by the second homology, and everything in second homology kind of represented by embedded surface. So the best guess is that if we can understand how surfaces sits inside a four manifold, we can actually then have a good understanding of the topology of the four manifold. And the third notion is exotic diffeomorphism. And by exotic diffeomorphism, I mean that a pair of diffeomorphism from X to X that are topologically isotopic, but not smoothly. So these are the three interesting phenomena that are very much interest of study for most of the four manifold topologists. And why they are interesting, there is this very remarkable result actually. So this is in early 90s. So in 1960s, Wall discovered a remarkable result. By the way, if I say just Wall, that would not be fair because I'll be talking about these three different categories. So for all generality, there is Perron and Queen also involved. So what they proved, essentially, they proved that if X is simply connected, then any of the above exotic phenomena disappears after sufficiently many stabilizations. So what do I mean by stabilization here? By stabilization, I mean that I start with X and I fix a four manifold, simply connected four manifold, and fix one of the phenomena, let's say either a pair of surfaces or a diffeomorphism or a smooth structure. And then if I connected some that with a few copies of S2 cross S2, and extend those notions through, like, let's say identity in S2 cross S2 component, then after a finite number of stabilization, that phenomena kind of disappear. And this is like a very, very surprising and remarkable result. So this is also like the proof of this kind of involve and have relation with the proof of H-cobordism theorem. So I'm not going into the proof of this observation. But then that arises the question now that okay, fine, like this is happening now, what can I say about the N? So the main interest is that what is this N, or how do we bound such N? So one of the big open problem in low dimension in four manifold topology is that so this is the open question, is that does a single stabilization enough? So that means saying that if you start with the exotic phenomena and you connected some with S2 cross S2, does it always disappear? Also, I would like to thank, I don't know if Peter is in the audience or not, but when I was a grad student in first year, Peter told me about this problem. I don't know whether he ever thought that I will ever contribute anything on the problem or not, but when I asked him a problem, he kind of gave me this problem when I was in my first year of grad student.
Peter would be here, but he's at ICERM.
Oh, okay. Yeah. Anyway, so So that the thing is that almost all the nice examples that we know so far about this kind of exotic phenomena that kind of satisfy this favorable conjecture or open problem that a single stabilization kind of vanishes. So just a small remark is that up to 2019, all examples or all exotic examples vanishes after a single stabilization. Okay. So something interesting happened in 2020. Definitely, I'm not talking about COVID here, but other than COVID, something interesting happened in 2020 that kind of changed my life. So in so in 2020, Kronheimer Moroka, and also independently David Baraguglia and Hokuto Kono they came up with a very interesting construction of an exotic diffeomorphism. So they construct exotic diffeomorphism. And let me explain this construction a little bit, because this is important for the remaining of the talk. So they generalize the notion of Dent twist and show some kind of exotic behavior. So let's talk about Dent twist for a moment. So Dent twist. So let's try to visualize the picture, and then we can write down the corresponding math. So what happens usually for Dent twist is that you map an annulus to an annulus by a diffeomorphism where this curve now goes a curve with a twist. Okay, so what happens? So let's try to write down the underlying math here. Is that we can think of this annulus as the time cross S1 to 0, 1 cross S1. And then at each time t, we have a fiber that is a circle S1. And what is happening is that we are kind of mapping that t is to t comma alpha ts, where alpha is now a non-trivial loop in the space of diffeomorphism of S1, where alpha is a non-trivial loop in the space of diffeomorphism of S1. So this is the abstract way one can define a Dent twist in 2 dimensions. And since this alpha is non-trivial, that is not null homotopic, we know that this diffeomorphism is now no longer isotopic to identities relative to the boundary. So then we can generalize this Dent twist, the notion of Dent twist, even for 0, 1 cross S3 to 0, 1 cross S3. Now the interesting fact is that the pi 1 of the space of diffeomorphism of S3 is homotopy equivalent with SO4. That's a famous celebrated result by Hatcher. So in particular, pi 1 of this space is Z-mod 2. So there is a non-trivial element. So we define the Dent twist as we take this non-trivial element and we correspondingly define the Dent twist by twist along this non-trivial loop. Okay, so any question up to this point? All right, so we'll be using this notion of Dent twist soon to answer a question related to the exotic surface and stabilization. So now let's talk about that part. So exotic surfaces and stabilization. Okay, so let me define again the notion of exotic surface. So a pair of compact surface sigma and sigma prime in 4 manifold X with boundary sigma equal to boundary sigma prime in boundary X are called exotic if there exists a topological isotopy of X relative to the boundary that takes sigma to sigma prime, but not smoothly. So this is the general notion of exotic surfaces. Now, as I said that before, that understanding surfaces in four manifold theory is historically important because various remarkable results says that somehow the topology of a simply connected four manifold determined by how surfaces sits inside the four manifold. Sorry, is there a question? Okay. So various technique has been used to understand exotic surfaces in four manifold. So various techniques such as I think the first technique that has been used to understand exotic surfaces was Donaldson's invariant. And then later Seiberg-Witten came to the picture, so Seiberg-Witten invariant. And then Heegard-Floer came, so Heegard-Floer theory. And also recently various other people use symplectic and contact geometry as well. So symplectic and contact geometry and Anubhav homology. So all these theories has been used so far to understand exotic surfaces. So one drawback about all these theories is that in all the examples that they have been used, that once we connected some with S2 cross S2, somehow these theories is not known to detect those phenomena after stabilization. That means that in most of the cases, those theories becomes trivial after connected sum with S2 cross S2, and for that reason, even though we have developed such a huge class of theory to understand exotic surfaces, somehow it still could not answer the question of walls, that whether single stabilization is enough or not. Okay. So this is one side of the story, but let me talk about a result towards the positive direction, that why there are some people who actually believe that the single stabilization is enough, and why such thing is true. So this is a theorem, and this is also a very recent theorem, I think. If I'm not wrong, it's 2018. So this is by Dave Oakley, Yoon-Ki Kim, Paul Melvin, Danny Ruberman, and Hannah Swartz. Okay, so what their results is that so in this proof they use the light bulb trick. So using 4D light bulb tricks, they prove that a pair of exotic connected surface in non-characteristic homology class with simply connected complements become smoothly isotopic after a single stabilization. So this is a very interesting result. So there are results saying that almost all the nice examples actually become by using this 4D light bulb theory actually become smoothly isotopic after a single stabilization. And the proof is very beautiful. Like if you are a grad student, I definitely recommend you to once like go over the proof. It's a very small paper, 3-page probably, but the proof is very beautiful. The best thing about is that I didn't know this result, and that's the reason I didn't get distracted by this result before. So this is the positive direction of the stabilization story, and we kind of produce the first counter example of this story. So now let me say about our result. So use black maybe. So our theorem. So this is joint work with Jianfeng Lin and myself. So we prove that there exists a link L in S3, which we can think of boundary of punctured K3. So the circle over K3 means it's punctured. So this is means it's punctured. That bounds a pair of disks, let's call them DL and DL prime, that are topologically isotopic but not smoothly relative to the boundary. Moreover, they remains exotic after a single stabilization. So any question?
Probably you'll say this, do they become exotic? I mean, do they become standard after 2?
I don't know. That's a very interesting question. I don't know.
I mean, this is great, fantastic.
Yeah, I wish. Okay, so I know that after 22, it's not 20. I thought 19. I think I know that after 19 stabilization, they are smoothly isotopic. I don't know about 2. I believe that it's not true. Even 2 is not what. So let's compare these two results for a moment. The only difference between these two results is precisely this part, that connected.
Actually, Anubhav, I have one more question.
Sorry, yeah, go ahead.
And what about a twisted stabilization like CP2 and CP2 bar?
Oh yeah, then they are diffeomorphic. That's correct. So yeah, so I'll talk about the proof, and you can see that the proof, like that the proof is telling you that like why it works for S2 cross S2, and like what kind of other problem occurs in other examples.
Okay.
Yes. So any other question before I kind of sketch the proof of this? So rest of the talk I'll be giving you a very brief sketch of why you should believe my claim to be true.
Are you going to say more about the Dane twist along the three spheres that come into the proof, or is that?
Yeah. That will come now. So yeah. So as I said, that the proof kind of lucky, I guess, that I was just reading one paper and I kind of have this problem in my mind, and I was trying to come up with a new proof, and I kind of like, I realized that, okay, this is possibly doable. So sketch of the proof. So the whole proof is, I feel, very simple if you see the right picture. Like, I think that's kind of the four manifold topologies, that once you see the right picture, the proof is almost obvious. So let's try to visualize the correct picture in this framework, that what is the pair of surfaces. That's the important thing, that once you see the two pairs, you can see, yeah, that obviously it has to be true then. So sketch of the proof. So okay, so let's recall that how we can construct a punctured K3. So a way of constructing punctured K3 is our most useful way is to use Handel calculus or Kirby calculus. So in that framework, we start with S3 cross I. So this is, let's say, we start with S3 cross I. And then we attach a bunch of two handles on top. And we build up a cobordism from S3 to S3. And then we cap it off with a 4-ball. So this is one way of seeing the punctured K3. So for simplicity, we just extend these handles so that it lands in the boundary. Okay. So the first observation is that the attaching spheres of this pair of two handles are the link L. So for us, the link L is nothing but, so let's say we just use 22 two handles. So the 22 attaching spheres are essentially that is the link L. Okay. And then obviously you can see that a pair of the exotic, one candidate of this exotic pair would be the DL is nothing but the core. So the core disks, or let's say the core of the two handles. Okay, so this is one pair. Okay, now let's come to the next part, that how do we see the other one. So as I said, that we just talked about Dane twist before, and as I say, I haven't finished the story. I just said Dane twist is interesting, and I said Kronheimer and Moroka did something, but I didn't say what exactly they did. So here is what they did. So on S3 cross I, we can define the notion of Dane twist. So that means we can apply our Dane twist in this part. If we do such, then what happens is that this Dane twist kind of twist this part of the two handles in such a way, and remains, everything else will be as it is exactly, nothing changes. So DL prime would be just apply Dane twist on each of these disks. Sorry, question? Okay, sorry. So this is our DL prime. Okay. So now, first of all, notice that these two pair of disks are topologically isotopic, right? Because I can think of this is just extending the Dane twist as an identity in this part. So for that reason, I can know now that, so the result of Kranich and Cooper's, and also a recent result by Orson and Powell, this says that the Dane twist delta on punctured K3 is topologically isotopic to identity. Since it's topologically isotopic to identity, that means then this image is topologically isotopic to this. So now the difficult part is to prove that they are not smoothly isotopic. So now claim they are not smoothly isotopic. And moreover, as I say, we now want to say something about the stabilization. So I can say that they are actually not smoothly isotopic even after connected sum with S2 process. So I can think of that I can connected sum, since everything is simply connected, I can connected sum anywhere I want. So I can think of that I connected some a copy of S2 cross S2 up here in that 4-ball region. So I can think that now, like let's like kill 2 birds with 1 hit. That proving that they are not topologically isotopic in punctured K3 connected sum S2 cross S2. And if we can prove that, then we are done. Okay. So okay, so any question before moving forward?
Just a silly question.
Yes.
Are you applying the Dane twist to only one of the chords or many of them?
No. Sorry. Repeat again.
Your picture suggests you're only applying the Dane twist to one of the.
Oh, no. Yeah, I'm applying to everything. Sorry. So like the picture would be very messy if I try to draw all the Dane twist. So for simplicity, I draw here, but here, like I just apply the Dane twist on all the disks together. So DL prime is just that you apply Dane twist on all the disk at the same time. That would be your DL prime. Is that give you your answer?
Yes, thank you.
Okay, great. Sorry. Yeah, I just draw it for simplification, because if I try to draw more Dane twist, it will look messy. So yeah. So let's just erase this part. Okay. Now we are good. All right. Okay. So now we'll use some kind of obstruction theory first. So okay. So the proof is essentially we assume that they are smoothly isotopic, and we come up with some contradiction. Okay. So let's say that let's assume DL and DL prime are smoothly isotopic. Okay, and now we try to come up with some contradiction if that happens. So if they are smoothly isotopic, so what I can do is that I can actually, so I have this diffeomorphism delta on K3 connected sum S2 cross S2, punctured K3 connected sum S2 cross S2, right? So if it is smoothly isotopic if these two pairs of disks are smoothly isotopic, I can do some further isotopy on delta and assume that the delta restriction on the boundary S3 union the disk DL is precisely the identity map, right? So this is, I can always assume. I just do some further isotopy and assume up to smooth sense that delta is precisely pointwise identity on the boundary S3 and this union of two handles. Okay. So now let's focus on each of the component of this disk. So a neighborhood of the disk is nothing but a disk bundle over D2. And we can also assume that up to isotopy in a neighborhood of this disk, this Dane twist, the diffeomorphism is actually a bundle map. So up to smooth isotopy.
It's a disk bundle over 22 disks.
Yeah. So yeah, like I'm for now, I'm just concentrating each component. So, but yeah, you are absolutely correct. So, and because they are disjoint, so we can talk all these things. So up to smooth isotopy, delta restricted on the neighborhood of DL, or you can restrict on each of the disk and its neighborhood. This is a bundle map. By bundle map, I mean that it is preserving the fibers. So bundle map, that is preserving the fibers. So everything is going smoothly right now. Okay. So since it's preserving the fiber, so that means what? That means then we have a map from the base to the fiber, or in a particular, I have a map from the base to the diffeomorphism space of the fiber. So this delta induces a map from D2 to the diffeomorphism of D2. In particular, everything is respecting the orientation. So in particular, I can also think of that this is the diff plus. And we know that the diff plus of D2 is nothing but SO2, right? And moreover, notice that the delta restricted on the boundary S3 is the boundary S3 is identity, and the boundary of this base space D2 lies in the boundary S3. So that means in this case, let's abuse the notation. Let's call this again the delta. So that means this is an element. This gives us an element of pi2 of SO2, right? Because this is the boundary is pointwise fixed to identity, and then this disk is kind of mapping to the diff interior of diff D2. So this is an element of pi2 of SO2. But this is what the interesting thing happen is that SO2 is same as homotopical equivalent to S1. So this is pi2 of S1, which is trivial. So that means this map is in some sense trivial. Or what does that mean? That means that we can do further isotopy. So this thing trivial implies that we can do further smooth isotopy on delta such that delta restricted on neighborhood of DL is now identity. So not only now delta fixing the disk pointwise, but now delta is actually fixing the neighborhood of the disk pointwise. And this is the interesting part, because let's come back to this picture again. So the way we constructed punctured K3 connected some S2 cross S2 is essentially this. We started with S3 cross I, we attach bunch of two handles, and then we take its neighborhood, and then we attach a 4-ball and then connected some S2 cross S2. But now if we assume that this pair of disks and this its image after the Dehn twist are smoothly isotopic, then we show that this delta map, the Dehn twist map, is precisely identity on this component, on this part. So let me try to write it down now. So this saying that delta on K3 connected some S2 cross S2 to punctured K3 connected some S2 cross S2 is smoothly isotopic, and everything is happening relative to boundary. You are not moving the boundary. Relative to boundary to a map of the form identity on K3 connected some F, where F is a diffeomorphism from S2 cross S2 to S2 cross S2. So the picture is following that we had punctured K3, and this is, let's say, the dent twist here, and we extend as identity, and we had S2 cross S2 here, and we showed that if those pair of disks are smoothly isotopic, then this diffeomorphism is smoothly isotopic to some map which is now identity on the K3 and some diffeomorphism F here. So just to make it a concrete closed manifold, we can always glue another copies of K3 here. So let's say K3 connected some K3 connected some S2 cross S2. We had the diffeomorphism delta here, and since everything is happening with respect relative to the boundary, so then that map delta becomes identity on K3 connected some K3 connected some diffeomorphism F on S2 cross S2. And now we'll use gauge theory to abstract this, that this is not true. So now our claim is that the delta cannot be of the form this map. So now using gauge theory, we'll say that the delta cannot be of the form identity connected some F for any F. So this is the strategy. So any question?
Well, I guess formally, are you also proving a one stabilization does not suffice result for the exotic diffeomorphism pair?
Yes, yes,
Well,
yes. Because this is because we are carry forward the information of S2 cross S2 here, which is not playing any part so far, but is still there. And all the argument works, like whatever I claim here, it works exactly in this frame of K3 connected some S2 cross S2. So if this pair of disks are so my claim is that if this pair of disks, so DL is smoothly isotopic to DL prime in K3 connected some S2 cross S2, that implies then that this dent twist on K3 connected some S2 cross S2 is smoothly isotopic to a map of this form, which is identity on this part, K3 connected some K3, and which is some diffeomorphism on this part. And then the final step is that using gauge theory and say that no, like dent twist cannot be, so dent twist here cannot be of this form. So is the strategy clear? Yes.
So that's why you need to connect some with the K3 on the other side rather than just like a 4-ball.
Yeah. So as I said, it's essentially the picture. It's just the picture. If you see the correct picture, the proof is there.
I guess what I'm saying is this is even stronger than saying that the dent twist on K3 connects on K3 does not become trivial.
Exactly. Yeah. It's much stronger. Yeah, you absolutely correct. And
that's by itself a strong result than one stabilization.
Yeah. It's much stronger than that. Yes. Yeah. So yeah, I promise not to give a technical talk, so I'll not say anything about Bauer-Furuta theory here, but just now let me tell a little bit about how we will show now that these two things are not smoothly isotopic. So given a diffeomorphism, we can always define this gauge theoretic invariant, which is spin 2 equivariant Bauer-Furuta theory. Okay. So here is the interesting fact that Jianfeng Lin proved that. So Jianfeng Lin proved that for family Bauer-Furuta, so that's why I write FBF, the pin to equivariant family Bauer-Furuta, this map is non-trivial. Okay, so this is what by proving that Jianfeng proved that this thing is not smoothly isotopic to identity, but we don't need that much information. We all need is that this map is non-trivial. By the way, here are some more technical information you need, but I'm kind of hiding those behind the scene. But if you are interested, feel free to ask me. So this is what Jianfeng Lin initially proved, and now we're gonna prove the second part. So let's compute the family Bauer-Furuta for this. So if you compute the family Bauer-Furuta of identity connected sum F. Now the interesting part is that there is a connected sum formula in gauge theory. And this works very nicely when one of the map is identity. So if this map is identity, this guy breaks into the regular Bauer-Furuta of K3 connected sum K3 smashed with the family into equivariant Bauer-Furuta of H2 cross H2 comma F. And then what we proved, one of our main theorem of the paper is that, so this is our main theorem of the paper, is that this guy is always trivial.
For any F.
Yeah, for any F. Any choice of diffeomorphism, this guy is trivial. And that implies then this whole thing is trivial. And that completes the proof because previous work of Jianfeng says that this is non-trivial and we prove this is trivial. So that means this is not true. And that means this is not true. So as I say, I'll not go into the proof of the technical gauge theoretic result here. And I feel that this is the best place to stop, and I'm happy to answer questions now.
Questions?
How important is it that you're using the K3 surface and not, like if I picked a random big enough orientable, the result holds?
So sorry, I can't hear. Can you please repeat?
How important is it that you're using the K3 surface?
Oh, it's somehow important because I mean it's not so any E2N should work, but it's essentially the family Bauer-Furuta computation. So yeah, the computation itself is not very good. Like we had to write pages after pages for the computation. So yeah. So this invariant works for spin 4 manifold, and then also you need some more structure on that. So for K3, we know nice structures that we exactly know how Bauer-Furuta maps work. It's essentially the Hopf map in the stable homotopy group. So that's a good thing. Or even any symplectic 4 manifold with B2 plus equal congruence to 3 mod 4 should work, I guess. But otherwise, it is a little complicated. Yeah, so we have worked out that part. And in fact, here is one interesting thing is that we actually showed that so if you think of this invariant just from the algebraic point of view, so from the algebraic point of view, this element for a spin simply connected 4 manifold, spin simply connected 4 manifold, this element lies in the stable homotopy group. So lies in the stable homotopy group into equivariant stable homotopy group when the signature is negative, and to here when signature is positive. So this element lies here, but now notice that what happened when we talk about force sphere. Now if we just talk about force sphere, everything vanishes. In other words, then this guy is just an element in the in the pi1 stable into equivariant group of, so this part vanish, this part vanish. So this is this. And this group you can construct essentially, and you can actually track down this element inside this group. So if you track down this element inside this group, so we prove that this element actually lies in, for S4, this element actually belongs to a subgroup which is Z mod 2Z. And we believe that this element can be non-trivial in fourth sphere. In other words, if we can find an F diffeomorphism S4 such that this element is the non-trivial element where alpha belongs to Z mod 2 is non-trivial, then that disproves Smale's conjecture. So that implies F is not smoothly isotopic to identity in S4. That means Smale conjecture in pi naught is false. So yeah, so we have developed this theory for a very general class of four manifold, and in particular, one of the most interesting results is that it actually could be non-vanishing in fourth sphere, because so far all the invariant that people have constructed in fourth sphere, everything vanishes. This is probably the only one which could not vanish. Again, the computation is so difficult. Sorry.
Have you tried for any particular app? Do you have a candidate?
I'm talking with people. For example, David Gavai gave me a candidate. I don't know.
I'll give you one too, probably the same one. I'll give you one another time. Probably the same one Dave gave me. Maybe.
Oh, I see. That's the same one. Okay.
Maybe
Yeah.
or maybe I don't know. I have one to give you.
Yeah, I'll be happy to actually to understand that construction. So yeah, so I think we have the invariant, but we do not have a nice candidate. So that's the problem right now.
Just for completeness, you didn't tell us what Kronheimer and Broca proved.
Oh, really? So, sorry. I think I just missed that part. Sorry, very bad. Oh, okay. I started talking and then I think I just missed my note. Sorry. This is happened when I write. I should have prepared slides. So Kronheimer and Moroka proved essentially, and Baraguglia Kono is that if you take connected sum of K3 connected sum K3 and you construct a Dehn twist here. So this Dehn twist is topologically isotopic to identity, but not smoothly.
So Lin just improved that to S2.
Yeah.
Improved it to that.
Yeah.
Great.
That's correct. Yeah. So all the motivation came from this paper essentially, and I was just playing around and I was thinking what else we can prove from there.
Any other questions? Let's thank Anubhav again. That's a great talk.
Yeah, thank you for coming by.